So section 2.1 is a continuation in our chemistry unit, Unit A. We finished up section 1 last lecture, and section 1.3 dealt with kind of how we have looked at matter over time. So as I mentioned, our early ancestors knew how to manipulate it with heat, melting, preserving, that sort of thing, but didn't really know what matter was made of. And then Aristotle came along and he said that all matter was made up of four elements, either earth, air, fire, or water. And a young upstart by the name of Democritus, he came along and said, you know what? No, I don't think so. I think that things are made up of these tiny little indivisible particles called atomos. And it turns out that he was right. But it wasn't until about 2,000 years after he came up with his theory that John Dalton actually looked and called the particle an atom and said that different substances were made up of combinations of different particles, and each particle had its own unique characteristics. Okay, and then from there we refined the model of the atom. Then came J.J. Thomson and Ernest Rutherford, and we are going to use the Bohr model of the atom in our study of chemistry in Science 10. And also in Chem 20 and Chem 30, you'll also primarily use the Bohr model, which is the planetary model, right? So we have our nucleus, and then we have electrons that fly around the nucleus in orbits. And those orbits can have a certain amount of electrons in them, and that's kind of how chemical bonding works when substances trade electrons or when they share electrons. Okay, and we'll get to that later on in our study of Unit A. Okay, so what we're going to look at today is we are going to look at how we arrange these atoms on something called the periodic table. So everything in our world, really, I'm gonna stretch it here. I'm gonna say everything in our universe is made up of only a few building blocks, right? So if we look at the modern day periodic table with all those letters and symbols on there, there's about 115 elements. Now, every day, well, I shouldn't say that, but all the time, we're manipulating matter and making new man-made elements. So the periodic table is always changing, but right now there's 115 elements. And elements, if you'll remember, are pure substances that contain only one type of atom. So for example, if I had a lump of pure gold sitting on my desk, that lump of pure gold would only be made of gold atoms. Okay. If I had a jar of pure, liquid mercury, right? It's a liquid metal. There would only be mercury atoms in there. So an element is a pure substance that contains only one type of atom, all right? And there are about 115 elements as we speak right now. Some of them are naturally occurring and some of them are man-made. Now, the elements are arranged on the periodic table in a very specific way, okay? And they are arranged according to their chemical properties. So how many electrons they have, how heavy they are, how reactive they are, okay? All of these things allow us to arrange these elements on the periodic table in some sort of order. Now, the person that came up with the first periodic table was a Russian chemist, and his name was Dmitry Mendeleev. And Mendeleev lived from the 1830s to the early 1900s. And if you'll recall, much of the research into atoms was being done in the early 1800s. So he was kind of right in the midst of it all. Now, there are about 90 natural occurring elements, which we find on the periodic table. About another 25 or so are man-made in laboratories. They don't last very long. They're very radioactive, most of them, and sometimes in under a second they decompose. So they're really kind of hard to study and look at. So Mendeleev, he started to arrange the elements that he was familiar with according to some of these chemical and physical properties that we've talked about. So again, their weight, their reactivity, kind of what they look like. Are they shiny? Are they lustrous? Are they dull? Are they? Do they have magnetism, magnetic properties to them? Can you bend them? So on and so forth. So there are many physical and chemical properties that he looked at, and he arranged these atoms in particular order. Now, this is his periodic table. Okay, this right here is his periodic table. And you'll notice that there are gaps in his periodic table because he didn't know about all the elements. So there were elements that he was unaware of, but he thought that eventually people would find these elements and fill in these missing gaps. So, I mean, not only was he brilliant enough to arrange all of the elements according to these physical and chemical properties, but he was smart enough to understand that he didn't have all the information, so he left space for scientists that were going to come after him to fill in those gaps. So the periodic table of elements can be organized into three broad categories, again, based on their chemical and physical properties. Now, what I would like you guys to do right now, please, is take out your data booklet. Okay, I'd like you to take out your data booklet, and I want you to flip a couple of pages, and page 6 and 7 in your data booklet. And what you'll notice there is the periodic chart of elements and ions that we are going to be dealing with. So we're going to learn all about what's going on this periodic table. But what I really want you guys to notice is on the right-hand side, on page 7, if you look at element number 5, boron, okay, and then you look right underneath it, aluminum, and you look beside it, silicone. Okay, so please, everybody take out that periodic table, flip to page 7. And what I want you to notice, starting at boron, you'll notice that there is a thicker line that is separating boron from aluminum and silicone from aluminum, okay, and silicone from germanium. And what it looks like is kind of a staircase. So if you look on your periodic table on page 7, you'll notice a thicker line at boron, and it kind of travels down your periodic table like this. What I would like you to do, please, is I would like you to highlight that. Okay? Now, everything to the left of that staircase, okay, everything to the left of that staircase is considered to be a metal. All right? So again, please, if you get a chance right now, grab your highlighter and write at boron number 5. So this would be boron right here on your periodic table. Okay, right to the left of it, you'll notice a thicker line, and below it, you'll notice a thick line, and it kind of forms a staircase that goes down, and it ends at number 85, astatine. Okay, everything to the left of that staircase is called a metal. Now, kind of hugging that line, boron, carbon, silicone, those guys are called metalloids. And they're kind of hard to classify, as we'll see in a second. But they're considered to be non-metals, although they have some properties of metals. So they kind of hug that staircase. And then everything to the right of that staircase is considered to be a non-metal. Right? Now you're going to notice at the very top here and here, hydrogen can be considered a metal and a non-metal. And again, we will talk all about what makes something a metal and what makes something a non-metal. Okay, hydrogen can behave in different ways. All right, so please on your periodic table, just pencil in there, highlight that staircase that separates the metals from the non-metals. Now, what makes something a metal? What makes something a non-metal? So all metals share the following properties in common. So if you take a piece of steel wool and you kind of shine up a substance and it is shiny, okay, lustrous, sometimes we call this. So sometimes another name for shiny is lustrous. You might see that word. Okay, it has luster. They're good conductors of electricity and heat. Okay, they are solid at room temperature except for mercury. Mercury is the only liquid metal at room temperature. What's room temperature again? We can measure it a couple ways. There's degrees Celsius, and then there's Kelvin. And when you get to Chem 20, you might use Kelvin. But room temperature is 20 degrees Celsius. Okay, that's considered room temperature. So mercury is actually is liquid at that temperature. It's the only metal that is liquid. Okay, they are malleable. So if you remember malleable, that means they can be beaten or rolled into flat sheets. Ductile means that they can be stretched into long wires. Okay, and they are located, like I said, on the left of that staircase. All right, so some examples that you might know from everyday life. Silver is a metal, tin is a metal, copper is a metal, okay, aluminum, lead, titanium, zinc, magnesium. A teacher may have burnt magnesium for you to see what a chemical reaction looks like. Okay, this one's wrong here. Steel is not a metal off your periodic table. Steel is actually a combination of different compounds, but iron would be a metal off of the periodic table. Now, non-metals make up a small portion of the periodic table. And again, non-metals are found on the right-hand side of that staircase that I pointed out, starting up at boron. Okay, so they're located on the far right. Non-metals can exist as many different states. Okay, so 5 of the non-metals exist at room temperature as solids, 1 of them as a liquid, and 11 of them exist as gases. Whereas metals are all solid except for mercury, right? Non-metals can be solid, liquid, or gases at room temperature. They are poor conductors of heat and electricity. They vary greatly in color, whereas metals are kind of shiny and silver. Non-metals can be colorless, they can be purple, they can be yellow, they can be all sorts of different colors. Okay, some are very, very, very reactive, as we'll see in a second, and some of them are unreactive, completely unreactive, actually. Okay, half exist as molecules. Okay, and again, a molecule is a connected group of atoms. So, for example, when we write oxygen, when we write the symbol for oxygen, what we actually do is we write it as O2. Okay, it actually does not exist by itself. The atom, the oxygen atom, does not exist by itself. It will partner up with another oxygen atom to form an oxygen molecule. Whereas if I were to write lead, for example, okay, lead, which is a metal, if I write lead, lead is written as Pb, and that's it. Okay, it just exists by itself. Nitrogen is another one. Okay, nitrogen will partner up with another nitrogen atom to form a nitrogen molecule, N2. Phosphorus will actually grab 3 other atoms, okay, to form P4. Sulfur actually exists as S8. Okay, it does not exist by itself. So many of them are connected into groups of atoms called molecules. And again, we don't find that with metals. And they are found on the far right of that staircase on your periodic table. Now, metalloids are weird ones. They're hard to classify. So we don't know really if they are, we don't know, they kind of have properties of both metals and non-metals. Okay, so we classify them as metalloids. So some have the ability to conduct electricity, but some don't. Some are shiny and lustrous, some aren't. So they're hard to classify. Okay, and we call them metalloids. So things like silicon, boron, arsenic. All right, so here is our modern day periodic table. And again, I asked you guys to highlight this staircase on your periodic table. Anything located to the left of this staircase are considered to be metals, and anything to the right are considered to be non-metals. And then we have these weird ones here on the right-hand side that just kind of hug the staircase, and they are the metalloids. All right. So that's not the only way that the elements are actually arranged on the periodic table. They are also arranged according to many other different chemical and physical properties. All right. So on your periodic table, if we take a look at the metals, what we find are the metals on the very far left-hand side. Okay, so way on the left, the furthest left on your periodic table, these metals are the most reactive. Okay, so these are very reactive. And what we find is on the way on the right, the furthest right on your periodic table, okay, these non-metals are not reactive at all. They are not reactive. And then right beside them, right here, these are the most reactive non-metals. And as we move toward the center of both the metals and the non-metals, we get less and less reactive. Okay, and again, this has to do with the idea of these electrons in different energy levels. Okay, and we'll talk more about that later on. Okay, so reactivity is one way to organize these elements. So is the mass. Okay, so if we take a look at mass on your periodic table, the elements, not only do they follow reactivity, but they follow, they're put into order according to how heavy the atoms are. All right, so as we get further down the periodic table from top to bottom, the atoms get heavier and heavier because they're made of more subatomic particles. Okay, so on our periodic table, the reason why it's called the periodic table is because each of these horizontal columns, or I guess rows, each horizontal row is known as a period. hence the periodic table. Okay, so we start up at the top, period 1, and as we move down, we increase the number of the period, okay, all the way down to 7. Now, these guys, which are found kind of on the outside of the periodic table, they actually fit right in here. If we were to do that, the periodic table would look really weird. So what chemists have done is they've taken out these and they've placed them kind of on the outside, but they actually belong right in here. Okay, period 6, this is a continuation, and period 7, this is a continuation. Okay, so this would have a real steep staircase, and then we would put these elements in there, and it would stretch it way out. So, just to make it nice and concise, we take those guys out of there. Okay, those metals out of there. Now, as we travel from left to right and we look at the vertical columns, these vertical columns are called groups or families. Okay. Now, we are going to spend the majority of our time in Chemistry 10 looking at Group 1, Group 2, Group 18, and Group 17 for the most part. Okay, we will look at other elements in there, but we have to learn the names of these families, okay, which I'm going to introduce to you in a second. And we have to know a little bit about them because many of the compounds we're going to be studying are a combination of elements from these particular families. Okay, so chemical families are groups of elements that have similar chemical and physical properties, and some of these are given special names. So the ones that we need to be really familiar with are Group 1, the alkali metals, Group 2, the alkaline earth metals, or just the alkaline earths, Group 17, which are the most reactive nonmetals, they're called the halogens, and then Group 18 are completely unreactive, what are known as the noble gases. And again, when we look at kind of atomic theory and we look at bonding and we look at chemical reactions, you're going to understand more about why these particular elements are in these families. Okay, now everything between Group 2 and Group 13, okay, all of these guys in the middle here, they're called transition elements. And then we have our lanthanides and actinides that are kind of taken out of this section right here. They would actually go right in here. Just makes the periodic table look really unwieldy. Okay. So group number 1, way on the left-hand side of your periodic table, this family is called the alkali metals. And the alkali metals tend to be soft. Well, they're metal, so they're shiny and silver in color, and they are very, very, very reactive. Okay, francium is the most reactive of the alkali metals, although lithium is pretty reactive as well, as is sodium, potassium, rubidium, and cesium. These are all very, very, very reactive metals. In fact, we cannot keep sodium or anything below sodium in its pure form in our lab anymore. I remember in university, we had some sodium in the lab, and it actually had to be stored in oil because it is extremely reactive with water, and it will actually react with the water in the air spontaneously, and it will explode. Okay, so it's really reactive. So it had to actually be kept in a special container, airtight container, and actually submerged in oil. Okay, and then as we move down, they get more and more reactive. The next group is called the alkaline earth metals. Again, they are shiny and silver. They tend to be a little bit harder than group 1. And although they are not as reactive as the group 1 metals, the alkali metals, they are still pretty reactive. So again, anybody who's ever seen magnesium ribbon burn, I showed you a quick video clip in one of the other lectures. It's quite spectacular. It's very bright. It's so bright it would actually kind of hurt your eyes. It needs a little bit of heat to get it going, but it still is quite a reaction. Okay, and you can see all of these metals are lustrous. Okay, and they can be pounded into sheets. They're a little bit harder than the alkali metals, but still not extremely hard. Okay, you wouldn't make a hammer out of magnesium, or you wouldn't make a knife out of calcium. Not only is it really reactive and it would spontaneously combust in the air, but it's also very soft.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
So you can see there that the alkaline metals are very, very reactive with water. As we move down that family toward the bottom, they become more and more reactive. Okay, so that's period or family number 1, the alkaline metals, and right next to them are the alkaline earth metals. Okay, that's period number 2. Family number 2. If we scooch all the way to the other end of the periodic table, we're into the non-metals now. If we take a look at group number 17, Okay, this family is called the halogens, and they are the most reactive nonmetals on the periodic table. Okay, so at the top there, you would have fluorine, chlorine, bromine, iodine, and astenine. And they will react with the alkaline metals to produce something called a salt. Now, you guys are familiar with table salt, right? Now, table salt is Na. Now, we find Na way on the left-hand side. It's an alkali metal. Okay, and Cl, chlorine, is a halogen gas, and together they form sodium chloride, which is table salt. But any group 1 and group 17, if we combine any of them, their byproducts would be salt. Okay, so for example, potassium fluoride, okay, that's also considered to be a salt. All right, because it's made of elements from those two families.
The halogens, column 17 of the periodic table. Each element with their own unique personality. Chlorine, a gas. Bromine, a red liquid. Iodine, a metallic solid. Let's take a look at each of them. The name comes from the Greek word chloros, meaning green-yellow. Chlorine gas was the first lethal chemical weapon used in World War I. It was cheap, simple to produce, and extremely deadly. In addition to blinding soldiers, it also reacted with the water in the lungs, forming hydrochloric acid. A simple gas mask with an activated carbon filter could prevent the effects of the gas. The Greek word bromos is the root of the name bromine. This red, volatile, and toxic liquid fumes a brown gas. It is one of two elements that are liquid under standard conditions. Being a liquid, its reaction with the metals was exceptionally violent.
Looks like bromine is one mean bro.
It should be no surprise that iodine comes from the Greek word iodai, meaning violet. This metallic solid sublimates to give an immense cloud of purple vapor. Iodine is also used as a disinfectant. You may know of it as tincture of iodine,
Yeah.
right? He knows. Halogen comes from the Greek words hal, meaning salt, and gen, to produce. They form compounds called salts, the most famous, of course, being
Salt.
sodium chloride. And that's exactly what each of these reactions were. They were redox reactions, in which elemental sodium gave up an electron and each halogen accepted an electron, making the atoms ions and giving them each 8 valence electrons. This was Chemistry in Context, and until next time, as always, stay safe.
It's just like bromine, mean,
I-
bro.
Yeah, I
like a mean, like a bro.
Joe, I understand.
Yeah.
And it's funny, it's just not the place. This is an educational video. Okay. See you next week.
Next time on Chemistry in Context.
Yeah. I'm just really worried about the GoPro. There were acidic, flamey things directly hitting it.
Okay, so that gives you a little bit of insight into the halogen gases, or liquids or solids, the halogens. Okay, and again, they are very reactive, especially when it comes to the alkali metals. Now, on the very far right-hand side of the periodic table, group 18 is called, the family is called the noble gases. And the noble gases are extremely unreactive and very, very stable. And again, when we look more at the makeup of the atom and we take a look at the subatomic particles in each atom, you will understand more why these particular families and the elements within them share certain characteristics. Okay, so we'll look more at that in the next lecture. All right, so all you have to know about the noble gases is they are found on the very far right-hand side of the periodic table. They are non-metals and they are very, very stable. So helium, neon, argon, krypton, xenon, and radon. Now, when we look at the periodic table and we take a look at an individual box on the periodic table, there's quite a bit of information in that box, and we're going to be using a lot of it in Chemistry 10. Okay, so you guys need to get familiar with understanding what information is contained within these boxes for each element. All right, so for example, here we have element number 22. Okay, it's the metal titanium. And this particular box tells us quite a bit of information. Okay, number 1, it tells us the atomic number. Now, as we study more about the atoms themselves, this atomic number will become important. It actually tells us how many protons are in the nucleus of this particular atom. Okay, Ti is the symbol for titanium. Now, some of these symbols don't, they seem like they don't belong. For example, lead, right? I referred to as lead earlier. Okay, lead has the symbol Pb. Now, you might think why? That has nothing to do with lead, but it's actually it refers to how you say lead in Latin. Okay, but this particular atom here, titanium, has the symbol Ti, so they relate quite well. Okay, there's the name and the atomic mass. So again, the atomic molar mass tells us how much an atom weighs, basically. Okay, this is derived by taking an average of what's known as the isotopes of a particular atom, and this sometimes we refer to this as the atomic molar mass because if we were to weigh out 1 mole of titanium, this is how much it will weigh in grams. Now, what's a mole? Okay, we will look at this later on in detail. Okay, we will look at what a mole is in detail later on. Okay, but this is called the atomic molar mass. And again, there are formulas that we will use where we need to know that. And then finally, what we find on the periodic table is we find the ionic charges. Now, on each box on your periodic table, you will find 1 or more of these charges, except on the noble gases. Okay, the noble gases do not form ions because they are stable. Okay, now an ion is a particle with a charge. Okay, so ions can either be positive or they can be negative. And again, we will talk about why this occurs later on. All right, but these charges will become extremely important when we start talking about a special type of chemical bonding called ionic bonding. Okay, what I would like you guys to do for the remainder of the time here is I would like you guys to work on pages 14 and 15 in your note package. Okay, so pages 14 and 15 in your note package, they will help you to get familiar with the periodic table. So on page 14, there's a chart where you have to go in and you have to kind of fill in the blanks. You're given a clue and you have to fill in the rest of the information, okay, according to the boxes on the periodic table. And then on page 15, there's kind of a story, and the story there are blanks there, and there are chemical symbols next to the blank. And what you have to do is just use your periodic table, and you need to find those symbols and just write in the name of those symbols from your periodic table.